Hello, everyone. This is Abdurrahman Sumayya. Today, I'm going to present you mapping in cycles dual domain PET CT synthesized framework with the cycle consist constraints. These are the authors for this paper, and the institution is the School of Biomedical Engineering, Shanghai Tech University. The problem statement: to address this limitation of the PET and CT image techniques when used individually, and to provide a framework that could generate both in PET and CT image from single scan, reduce the risk of radiation exposure without scanning CT. As you may know, that CT uses an X-ray scan to generate that image. The next thing is that generate accurate and consistent image for both for PET and CT modalities from a single scan. And the last thing is most existing work perform based image synthesis to construct cross modalities mapping only in the image domain without considering the projection domain, leading to potential physical inconsistency. Later, we're going to explain, there's a lot of definition, there's a lot of terminology that I'm going to explain about the image domain, the projection domain, so everyone's could be in the track. So here's the picture of the CT scan, and here's the picture of the PET scans, and here's the picture of the PET CT scans. As you can see, these pictures are different, and each picture have their own technique that is generated by the machines. So what is PET and what is CT? PET is the image provided information about the function and the metabolism of the tissues rather than their structures. PET images uses a radio tracer that is injected into the body and emits some electrons which are detected by the PET scanners. And on the other hand, is the CT image provide a detailed information about the body structure, but does not show the metabolic activities. Also, the CT image uses X-rays to produce a detailed image of the body internal structure, such as the bones and soft tissues, and use computer algorithm to reconstruct the 3D image of the body. Now I'm going to talk about what image domain and the projection domain. Image domain refers to anything that the representation of the signals and such as an image or video that in its 4 pixels form. Also, for contrast, for the image domain here in this paper, they refer to the PET image and the CT image, which are 2 different types of medical image acquired using different imaging modalities. On the other hand, the projection domain refers to the representation of signals that transform the space. This transform space is usually obtained through a mathematical operation such as a Fourier transform or wavelet transform. The projection domain is the signgram data obtained from the PET and the CT scans. A signgram is a 2-dimensional arrays of value that are represented in the attention of the gamma rays passing through the tissue's different angles. So we have there are many image domain, and we need to understand the differences between them. For example, here are the image domain that shows you the head of a person, while the projection domain looks like something like that. So we need to find a model that could take an image as this one and transfer it back to the image domain, and take an image domain, transfer it back to the projection domain. Next, I'm going to talk about the mapping and cycles. These are some of the terminology that they use in this paper. Mapping and cycles is a concept image synthesis that involves using cycle and consist constraint to generate image in 2 or more domains. The idea behind mapping and cycles is to ensure that the generated images are physically consistent with each other, even if they come from different domains. For example, if we have a pictures that is coming from this domain, projection domain, and we need to transform this back to this image domain, there will be no differences. And if we take it from this domain and transfer it back to this domain, we will have it in the same state that was here. The idea behind this mapping in the cycle to ensure that the generated images are physically consistent with each other, even if they come from different domains, as explained before. Also ensure that generated images can be transferred back and forth between domains without loss of any information. As you may know that in the medical field that we care about information and the loss of information, and we need to be precise about this one. So we could read the images for the patient and cure them accurately. This is the cycle consists dual domains, and as you can see, we have domain A which has an apple, and that generated over here. Then we have another domain which is B that's generated over here. And the explanation of the cycle consists dual domain cycle GAN is basically a model consists of two generator and two discriminator, which each generator and discriminator being trained in separate domain of images. The generator learn to transform the image from one domain to another domain, while the discriminator determine whether the generated images are real or fake. This kind of work that has been done many times, and they use it with this paper. Next, I'm going to talk about related work, previous studies and research related. One of the things that a previous study have done is the traditional PET-CT image fusion and deep learning based approach. And we will talk about the drawback of these techniques that they have used in the past and why this approach that the author provided is much better. The limitation and the drawbacks of the previous approach for the traditional PET-CT image fusion, the misregistration. Misregistration is basically a PET and CT image are acquired using different image modalities, which can result in misalignment and errors in registration. This could lead to inaccurate fusion of the image and affect the interpretation of the result. The second problem, the drawback for the traditional PET-CT image fusion is the limited spatial resolution. PET image have lower spatial resolution compared to the CT image, which can limit the accuracy of the fusion. This can particularly problem in the areas of which complex anatomy, such as the head or the neck. The other problem with this traditional PET-CT image fusion is the limited anatomical details. Basically, PET image have primarily provided a functional information, while CT provide anatomical details. Basically, CT provided the structure of the bones or the structures of the head or anything or any organ like that. The traditional PET-CT image fusion method rely on anatomical information from the CT image to guide the interpretation of the PET image. However, the problem is that the limited spatial resolution and other factors can affect the accuracy of anatomical information in the CT images. Another drawback and related to work is the deep learning based approach. The problem that we have with the deep learning and based approach is that the limited training data. As you may know that in the medical field, it's hard to get and gather data, and deep learning models tend to require a large amount of labeled data for training. However, the problem is that data can be challenging, and especially for rare diseases or imaging critical, hard to get it. The other problem that we have with the deep learning based approach is that the overfitting. Deep learning models sometimes they tend to memorize the training data instead of like generalizing the new data. This can lead to poor performance in a new data that the model have not seen before. The other problem that they have with this related work in the deep learning approach is that the domain shift. Deep learning model can also suffer from the domain shift, where the model fails to generalize to a new data that is different from a training data. This can be a particular problem in the medical imaging, where image protocols and equipment are very different between institutions. How the proposed approach differ from the previous studies. This approach uses cycle consist mapping between two domains And basically, this approach aims to generate a synthetic PET CT images that are realistic and accurately represent the underlying anatomy and physiological process. This achieved by training a pair of dual domain network that can convert image from one modality PET or CT to another back and forth, while maintaining the consistency between the original and the synthesized images. The motivation of the research. The motivation of this research to address the challenges the research have explored method of synthesizing the PET and the CT image that combine the strength, both the modality into single images. So what the researchers want to do is that they want to take out the burden of the patient to do two images and let them do one of the images. If they could eliminate the CT images, which use the scanning, which is use the X-rays, they could save a lot of money that is that's the patient will have to pay, and also reduce the patient from the risk of for the radiation. Also, another thing that this another thing for the motivation of the research is that this could potentially prove the accuracy of the sensitivity of the cancer diagnosis treatment planning, while reducing the patient healthcare provider from using these big machines or expensive machines. The main contribution for this paper proposed a new framework for synthesizing the PET and CT images. And basically what they do in this paper, they propose a new framework that synthesizes the PET CT images using dual domain network architecture with a cycle consist constraint. The framework aims to generate a high quality and realistic PET CT images while maintaining the consistency between the original and the synthesized images. The other thing that they want to do, the other thing that they contributed to this paper is that the demonstration of the effectiveness of this proposed framework through a comprehensive evaluation on multiple publicly available data set. Also, they included visual assessment, quantitative measurements such as the SSIM and the PSNR. And these are the measurement of the tests they have done in this paper, and we're going to talk about this deeply later in the slide. Also, the main contribution for this paper is to provide a new insight and advancement in the field of the PET and the CT images syntheses, and have the potential to improve the quality and efficiency of the medical images. One thing that I want to talk about is that here's the fourth outline. The first thing that is I want to talk about is the dual domain network architectures, and the second thing is I'm going to talk about the cycle consist laws, and the last thing is going to be the training and the evaluations. So what is dual domain network architectures? The author proposed a framework used two networks, one for the PET domain and one for the CT domain, to generate corresponding images for each modalities. The network are designed to capture the feature and the character of the corresponding images. Also, the author trained simultaneously to ensure the consistency between the synthesized images. The second thing is the cycle consist loss. The framework uses cycle consist loss function to ensure that the synthesized images are consistent with the original images. Also, they use the loss function. They use the loss function, which consists of two components: a forward cycle consist loss, which ensures that the synthesized CT image can be converted back to the original PET image, and the backward cycle consist loss, which ensure the synthesized PET image can be converted back to the original images. Lastly, the training and the evaluation. The framework are training the data set and the pair of the PET and CT images and the performance is evaluated in a separate validation set using both qualitative and quantitative measures, including visual assessment by expert radiologists and the SSIM and the PSNRs. Here's the detail of the proposed approach, and here's the framework. As we talked about it earlier, here's the dual domain consistency, stage 1, and the stage 2 is the cycle consistency. And also here's the framework that the author adopted, is that they have the PIR images and they have the PIR sign-ROMs, and also they have the CT images and the CT sign-ROMs. And you can see this, and you can see the relationship between these is that they use a forward projections going to the PIR images and filtered back projection going back to the PIR images. And also they use the same for the CT images. Also, they connected these projection domain network between two of these. For example, they have the PIR sign-ROMs and they have the CT sign-ROMs, and they connected these two images with the projection domain network. And also what they did is that they connected the image domain network between the CT images and the PIR images. What I'm going to talk about next is the dual domain consistency. As you see over here, here are the loss functions that they use for the dual domain consistency image domain for the CT images. The XPET is the input of the PIR images, and the XCT is the input of the PIR images, and the G image is the image domain network, and the GSYN is the projection domain, and the F is the forward projection, and F filtered back projection. The goal for this stage is to learn two mapping functions, one that maps PET images to the CT images, and the other that map CT images to the PET images. The mapping function are learned in the cycle consist way, which means that the output of the one mapping function could be used as an input to another mapping function. The result image should be similar to the original image, and also the author uses two loss functions to enforce this cycle consistency. And one of the functions that they use for consistency is the CT image. The other loss function they use for the image projection, which is relay over here. So what they have done is that they develop 4 models for each images. One for the image projections using the CT images. The second one, they use the image projection for the PIR images. And the third one, they use the image projection for the PIR sign-ROMs, and also, I'm going to repeat again. What they have done is that 4 neural networks and 4 models. One model trained the image domain with a CT image, and the second model used the image domain for the CT image. They use the image projection for the CT sign-ROMs, and the third one they used the image projection for the PIR image, and the fourth they used the image domain for the PIR the image projection for the domain PIR images, and the image projection for the PIR sign-ROMs. So they have developed 4 models that they are connected together, so they could use it to exchange the information back and forth between all the data. And this is for the first stage of the framework. The second stage is the cycle consistency, which there are 3 cycles: cycle 1, cycle 2, and cycle 3. Why they have developed a cycle 2, a stage 2 cycle consistency? The goal for this method is to synthesize the output per image that is in cycle consists with the input image with the CT image. This means that the synthesized per image could be transferred back to the input CT domain and also transfer image, and the transfer image should be similar to the original input image, to the original input CT image. To achieve this cycle consistency stage, they included two mapping, one from the CT domain to the PET domain, which we see over here. Second, they included a cycle from the PET domain back to the CT domain. And lastly, they used a last cycle to include the cycle consistency loss function to ensure that the synthesized PET image is consistent with the input CT image.
Sorry to interrupt here. I just want to have a quick reminder. You have like 4 or 5 minutes left, but it seems like you still have a lot of things to go
Yes.
and move quickly.
And the reason, yeah, sure. The reason I'm reading it through this one because there's a lot of terminology that I need to
yeah, sure, yeah.
So let's talk about actually the model that they use. They use RN unit networks architectures. And the reason they use this one is because they want to capture the global information as an image domain synthesis network. Second, they use a fully connection network, FCN. And the reason they want to use that because they want to keep the most of the details information as a projection domain network. Lastly, they use a PyTorch platform from and use the NVIDIA Titan RTX 24 gigabytes. And they use the Atom optimizer for the stage 1 and the stage 2, and these are the numbers. The hyperparameter are set to be 0.5, and they have a train 600 times of EPCOs for each method. So I think they totally run like 2,400 EPCOs for all the training models. The data set. So the problem that I have with this paper is the data set. They don't explain a lot of things about the data set. What they just explain that they have collected 65 pair PRANE, PET, and CT volumes and they use this system called UExplore PET CT system scan. Sorry. And the pre-processing for this, what they have done is that they take the 20 slices of each volume in Excel view with the brain tissues, and they slice them from 65 to 1300. And also the image that they feed to the models is 128 to 128. And then intensity range is normalized between 0 and 1. Last thing, the way that they train their model, they use 1,000 samples for the training, 60 for the samples and samples at the validation, and 240 for the training set. Next, I'm going to talk about the SSMI, the PSNR, and the NRMSC. These are the evaluation metrics that they use in this paper. Before I go ahead and explain these results, I want to just make sure that what is the SSIM is basically the structural similarity index measurement. The second one, the PSNR, is going to be the peak signal to the noise ratio. The third one is going to be the NRMSE, which is going to be the normalized root mean squared errors. Actually, as you see over here, they have compared their method with state-of-art method. They use the unit, the R unit, the P2P GAN, the cycle GAN, and mid GAN. And you can see their method outperform from the PET to the CT, all these state-of-art models. And from the CT to the PET, they outperform the PSNR and the NRMSE, but the cycle GAN beat them with 2% from the CT to the PET. Here they have compared the state-of-art images with other models. This is their models, and this is the other models. This is the model coming from the CT. The less blue dot means that the less errors that they have in their models. As you can see, other models have much more of blue, which is mean a lot of errors. The only thing that could be compared to this their method is the cycle GAN, because the cycle GAN used the bidirectional transform backbone from the PT into the CT. Also, they have published another way of measuring their method. You can see over here that they have used the base and the base S and base SC1 and the base SC2 and the base SC1. Quickly explaining about this base is that base is donate to the only using supervision loss in the main task, and the S donate to the using the secondary task to help the main task. The C1 donate to the image domain cycle consist loss, and the cross domain cycle, and the C2 donate to the cross domain cycle consist loss in the stage 2. And you can see over here that the base plus S1 plus S2, they have achieved a lot of good results. The conclusion for this paper, I think this paper is really good. They have the potential application they could develop for the medical field. And also, one thing that I think I like about this paper is that they extend the framework to include other models. The strength and the weakness for this paper, the strength is innovation framework, use cycle consist constraint, and extensive evaluation. The problem that I have with this paper, as you said before, is that the data set, they didn't explain anything about the data set and where they got it from. And also, they have a limitation of analysis of their models and details. Future directions, I would love to see this model being used with different machines and also being used with a different data set. Also, I would like to see that this model has been incorporated in the clinical expertise, and also maybe explain more about the clinical approach that they want to develop for the medical field. The rating for this paper, I give it 1 because of the state of art and the way that what they have done. They focus on more on the framework rather than their model and network architectures. And thank you for having me.